Thank you. So first of all, I would like to thank the organizers for the invitation. First of all, I want to introduce the main problem I'm going to discuss. But before, I want to give you some motivations. So the first part of the talk is dedicated to enriched curves. So let me give some motivation. Introducing the problem I will discuss. So assume that we have a smoothing of another curve. So let C over B be a smoothing of another curve. And everything I will say will be over C. And this means that we have a family of curves over a one-parameter base, B. So we have a C, a surface over B. And here we have a special point 0. And so the fiber over 0 is another curve. And the other fibers of the family are smooth curves. So this is the picture. And I also assume that the surface, which is the total space of the smoothing, to be a smooth surface. So a natural question to ask is the following. So assume that we have an object defined over the general fiber of the family. So think about, for example, Weierstrass points on smooth curves. So we can consider the generations of these objects to the special fiber. So a natural question is the following. Do the limit only depends on the special fiber of the family? So in general, the answer to this question is no. So in general, so the answer is no. And so with this motivation in mind, Lila Mayneau in 1998 introduced the following definition. So this is by Lila Mayneau. So introduced the notion of enriched structure on another curve and an enriched curve. So an enriched curve consists of the data of a pair. So C is another curve, and L is a bunch of invertible sheaves on the curve. And so if C is the union of component CI's, I goes from 1 to gamma. So L is a set, is a bunch of line bundle. We have one line bundle for each irreducible component, subject to the rule that Li is the restriction of OCCI to the special fiber, where C for some smoothing C of C. So since the total space of a smoothing is a smooth surface, here we have a Cartier divisor defined on the surface, and so this gives you a line bundle on the curve of degree 0. Okay, so this is the notion of enriched curve. And I want to stress here that we have, behind the notion of enriched curve, we have a discrete datum, which is given by the irreducible components of the curve. But we also have a continuum datum, because we are parameterizing, in some sense, all the possible deformations of the curve to smooth curves. So this is quite important to consider problems like, for example, the generations of Weisser's points. So the main theorem which was proved by Laila Maynaud is the following. So she constructed a moduli space of such objects. So she proved that there exists a blow-up EG bar of MG bar, and this is the moduli space of the linear Mumford stable curves. So she constructed a blow-up EG bar over MG bar, and an open subset EG of EG bar such that this open subset is a moduli space for genus G, stable enriched curves. So an enriched curve is stable if the nodal curve appearing in the pair is stable, and has genus G if the curve has genus G. And so she produced this blow-up, and this blow-up is quite explicit, as I will explain in a while in 2 examples. So before giving you the flavor how she constructed this blow-up, let me just give you 2 definitions. So a graph gamma is biconnected if it is connected and if it remains connected after the removal of any one of its vertices. So, and remains connected after the removal of any vertex. So this is the notion of biconnected graph. And so let me give 2 examples where I will explain in how is this blow-up, how does it work. So this is the local picture of this blow-up in 2 examples. So assume that we have a curve C, which is a curve with 2 components and 3 nodes. And so if we look at MG bar, so locally around the point parameterizing C inside MG bar, we have a polydisk, which is the base of the deformation of the universal deformations of the curve C. So it is C3G minus 3. And so we can look at a C3, a distinguished C3 inside C3 3G minus 3. So this C3 parameterizes deformations which smooth some of the nodes. So we have 3 nodes, so this amounts to be a 3-dimensional complex space. So we have this picture. We have this C3. And the universal family over this C3 works as follows. So over the origin, we have the curve itself. And over the generic point of the three axes, we have a curve obtained by smoothing one of the nodes. So we have an irreducible curve with two nodes. And over the generic point of the three coordinate planes, we have an irreducible curve. OK, this is a local picture of mg bar locally around this curve. So the minor blow up, so the blow up performed by Minot do the following. So define over mg in mg bar the locus m gamma. So m gamma will be as a set the locus of stable curves whose dual graph is gamma. And so the recipe to get the blow up performed by Minot is the following. Blow up the loci m gamma bar. So I will take the closures of these loci starting from the ones of maximal codimension. Subject to the rule that gamma has to be biconnected. So this is the general rule that you can apply to get the Minot blow up. So coming back to our example, so this in this C3, we only have one locus parameterizing curves whose dual graph is biconnected, namely the origin. This curve has a dual graph, which is this graph, which is biconnected. And so we blow it up, we blow the origin up, and we get this P2. And so this P2 amounts to be the fiber of the blow up, EG bar over MG bar, over the point parameterizing this curve. A different picture we can get if we consider a different curve. For example, so let me give you a second example of a curve which is a triangular curve. So again, we have a distinguished C3 parameterizing deformation, smoothing some of the nodes of the curve. But this time, okay, over the origin, we have the curve again. But this time, over the three axes, we have a curve obtained by smoothing one of the nodes, which is a banana curve. So this, and over the three coordinate planes, we have again an irreducible curve. So this example is quite different from the previous one, because if we look at the locus parameterizing curves whose dual graph is biconnected, we don't only have the origin, but we also have the three axes, because the dual graph of this curve is again biconnected. And so the blow up performed by Minot this time blow up first the origin. So we get again a P2. But since the three axes parameterize curves whose dual graph is biconnected, we also have to blow up the street transform of the three axes. So we finally get the blow-up of P2 at 3 points as a fiber. So this is the picture we get. Okay, so another problem I want to discuss is the following. So we have this moduli space of enriched curve. So I would like to consider, or I would like to produce a modular compactification of such space. So okay, this seems quite an interesting problem, but I will consider a weaker problem, which is the following. So a natural compactification is the one produced by Minot by considering the block of mg bar. So EG is containing in EG bar. So I want to give a description via toric variety, a toric description of the fiber so EC bar, where EC bar is simply the fiber over the curve C of the Minot blow-up. So we have this diagram, and EC can be viewed as a compactification of the variety parameterizing enriched curves over a fixed nodal curve. So I will give you a description of this compactification. To do that, I will use tropical geometry to solve this problem. So tropical geometry, which will be the second part of the talk, in particular tropical curves. So I will follow the approach. Yeah, the fiber. Yeah, this is a point. Yeah, this is the fiber over C. Yeah, and okay, I will go to tropical curves to solve this problem. And so I will follow the approach due to Branetti, Melo, and Viviani, and Caporazzo. So for me, definition, a tropical curve is the datum of a graph and two functions. So omega is a function going from the set of vertices of the graph to z non-negative. It is a wave associated with each vertex, and L is the length function going from the set of edges to positive real numbers. So it is a metric graph, and so we can consider also stable tropical curves. So what is a stable tropical curve? So it is stable if whenever a vertex is such that its wave is equal to 0, then its valence, the valence of this vertex, is at least 3. this is the notion of stable tropical curves. And we also have the notion of the genus. So the genus actually of the weighted graph, omega and gamma and omega, is given by G, which is the first Betsy number of the graph plus the sum of the weights of the vertices of the graph. So this is the notion of genus. So once we have a notion, the notion of tropical curves, a natural question is, can we produce a moduli space of such objects? So this was constructed by Caporaso and Branetto, Melo, and Viviani. And so the construction is as follows. So as a first approximation, we want to construct a moduli space for any given weighted graph, gamma and omega. We want to parameterize all the tropical curves whose underlying weighted graph is omega and gamma. So it is quite simple because for any gamma and omega, we have, so the only thing that can vary in this problem to find all the possible tropical curves with underlying weighted graph gamma and omega is the length. Okay, so we have this space, C gamma and omega, which is, okay, so R to the E of gamma positive up to the group of automorphism of the weighted graph. So it exactly parameterizes all the length we can put to a weighted graph to transform it in a tropical curve. And so we can define mg trop as the union of these cells, where gamma and omega is stable of genus G. Okay, this is quite a naive definition. It doesn't tell you so much about how these cells are put together, and so there is an alternative description that we can use to better describe the topology of this set, of this space. We can do the following. So we can take the closures of these cells. So the closures are obtained possibly by taking 0 real numbers. So it is the closure in R greater or equal to 0, E of gamma. Modulo 1, an equivalence relation that tells you how these cells, these closures, are put together. And this equivalence relation is the one induced by specializations of graphs. And I will tell you exactly what it is. So we say that gamma and omega specializes to gamma prime, omega prime, if gamma prime is obtained by contracting edges of gamma, and omega prime is induced by omega. So for example, if we have this graph with 1, 0, and 1, 1, 0, so a specialization of this graph, for example, consists in contracting this edge. So we have a specialization which is obtained by contracting this edge. So we get this graph with 2 vertices and 3 edges. So here we put the weight 0. And since these 2 vertices are converging to this vertex has weight 2, which is the sum of the 2 weights. Okay, this is the notion of specializations of graphs. And so the equivalence relation appearing here is as follows. So assume that we have a graph gamma prime, omega prime, specializing to gamma and omega, and another graph gamma double prime, omega double prime, specializing to gamma and omega as well. So what we can produce is the following. So we have a natural embedding of r to the e of gamma greater or equal to 0 inside r to the e of gamma double prime greater or equal to 0, because this graph is specializing to this other graph. So this vector space is sitting naturally inside this other vector space, and we can do the same for this other graph. And so if we have 2 points in here and in here, I declare that they are classes modulo the automorphism group of the weighted graphs are equivalent if and only if there exists a point in here going to Q prime and to Q double prime. So this map is J1, this map is J2. So J1 of Q is equal to Q prime, and J prime of Q, J1 of Q is Q prime, and J2 of Q is Q double prime for some Q. So this is the equivalence relation that we put in this space to get something interesting as a topological space. As indeed, what Branetti, Melo, and Viviani proved is the following. So MG tropical is a sticky fan. So I don't want to precisely define what a sticky fan is, but roughly speaking, a sticky fan is obtained as we did for MG tropical. Namely, we have polyhedral rational cones acted upon by finite groups, and so we take the quotients, and their closures are put together along the boundaries. So this is a general rule to get sticky fans, and so MG tropical was proved to be a sticky fan. And okay, this is what I wanted to say about tropical curves. And now I will go to the third part of the talk. I want to introduce enriched tropical curves. So the key definition I want to introduce is the following. So I introduced enriched curves and tropical curves. So I want to introduce the notion of enriched tropical curves that will be very important for us to describe, I remind you, the fiber of the blow-up produced by Lila Maynot. And so the definition, the key definition is the following. So an enriched structure on a graph gamma so is a preorder. So I remind you that a preorder is a binary relation which is reflexive and transitive, but not necessarily symmetric. So it is a preorder P on the set of edges of gamma such that, so it is a recursive definition. So we have the first case, which is the following. If E of gamma has only has 0 or only one edge, so the preorder P is trivial. Second part, if gamma is biconnected, then we claim that there exists a subset S of the set of edges, E of gamma, which is a lower set for the preorder, which means that E is less or equal in P to E prime for any E in S and any E prime in the set of edges. And such that, so we can consider the graph. So if we consider gamma mod S, it is the graph obtained by contracting all the edges in S. So this is given by the contraction of S. So P restricted to the edges of this graph is an enriched structure. No, yeah, if it is a reflexive binary relation and transitive, not necessarily symmetric. So you can have some E that is less than E prime that is less than E, but E is different from E prime. We can do that in a preorder. And in this case, I will say that E is equivalent to E prime. Okay, but this can happen.
So any two elements are comparable, or is it partial?
It's partial, yeah.
So some elements are not comparable?
Yeah, could be, yeah. Yeah. No, because they can be no any could be equivalent. Any element of S is equivalent to the element of S in particular. by the definition. So let me give you an example to be clearer. Okay, just let me, the third part that is missing, if gamma is not biconnected, so the preorder P is the datum of an enriched structure on each biconnected components of the graph. And elements that belong to different biconnected components are uncomparable. Okay, I don't write this part, but each element that belong to different, if two elements belong to different biconnected components, they are uncomparable. Let me give you some examples how to compute these preorders, so examples. And let me give the example with the dual graphs of the curves I consider in the first part of the talk. So the first example is a graph with 2 vertices and 3 edges. So E1, E2, and E3 are the 3 edges. So it is biconnected, so it fits in the second part of the definition. So we have to choose this lower set. And for example, let me choose S to be the set E1. And so we contract the edge E1. And so we get this graph here. But this graph is not biconnected. So to define an enriched structure on the second graph, I have to use the third part of the definition. But in this case, it is trivial because we only have 2 edges, one of each belong to one biconnected component. So I will declare that E1 is less or equal than E2 and E3, but E2 and E3 are uncomparable. So we get the following preorder. And of course, we have 3 of these of such preorders. Of course, I have to choose one of the edges. Okay. But we also can choose as S the set E1 and E2. So if we choose this lower set, so again we come to a graph that fits in the first part of the definition. And so in this case, E1 is equivalent to E2, and E2 is less than E3, which is the edge that survived to the contraction. Let me give you another example, which is the second example that I considered in the first part of the talk. So the second example. So we have a graph, which is a circular graph. This is E1, E2, and E3. So again, I can contract the set consisting of one edge, for example, E1. But this time, I get a biconnected graph when I contract only E1. So I have to use again the second part of the definition. So I have to choose another lower set, this time of this graph. So for example, E2. And I will get a graph that fits in the third part of the definition. So in this case, we have that E1 is less than E2. and E2 is less than E3. And this time we have 6 possibilities for such rigid structures. Before we had pre-orders, and in this case we have 6 enriched pre-orders. So before we have also enriched pre-orders here. Okay, these are the key examples I wanted to introduce. And to state the main theorem we proved, I need another piece of definition. So I have to define, define. So first of all, we can define an enriched tropical curve. So what is an enriched tropical curve? Is a gadget consisting of gamma, omega, and L, and P. So this is a tropical curve. And P is a preorder on gamma, is an enriched preorder on gamma, so an enriched structure on gamma. And we have a compatibility condition, which is as follows. So such that whenever we have 2 edges that are one less or equal than the other one, then the length of E is less or equal than the length of E prime. And if they are equivalent, this happens if and only if the 2 lengths are equal. So one part of the main theorem I will state is that we can construct a moduli space of enriched tropical curves. But before, I have to tell you what are the cells of this new moduli space. So we can consider K of gamma, omega, and P. So it sits inside this R E of gamma, positive. So if this guy has coordinates xe, namely an element in here can be written as xe dot e. It is a typical element in here. So this cone is obtained as follows. So it is the vectors such that xe is less or equal than xe prime if e is less or equal than e prime with respect to p. And we have that the equality holds if and only if the two edges are equivalent. So this is the cone. So let me come back to the 2 examples to illustrate how these cones are constructed in the 2 examples. So in this example, the first example, which was the one of the graph with 2 vertices and 3 edges. So in this case, so we have 2 edges. So we have it R3. And inside this R3, we have all the cones that we can get by varying P through all the enriched structures on the graph. So now in this case, we have this R3. So we can draw a picture as follows. So I will draw a section of this R3. So this is the origin. This is a section of the R3. And in this case, since we have these 3 possibilities for the contraction of one edge, so this means that these conditions in this case, became the condition that x is less or equal than y if R3 has coordinates x, y, and z, and x is less or equal than z. So one coordinate is less or equal than all the other ones. So we have this, this partition of R3 positive in cones. Okay. And in the other example, so the picture is different because we had 6 enriched preorders. So again, in the R3, with coordinate r, x, y, and z, we have a different picture because in this case, all the relations giving rise to the cones, k, gamma, omega, and p, are as follows. So we have 6. In this case, we have 6 maximal cones. And again, I will draw a section of this R3. Okay. So quite a remarkable proposition is the following. As you are, it is happening in these 2 examples, the R3 positive is decomposed in cones, in the cones k, gamma, omega, and p. And this is a part of a proposition that actually R E of gamma positive can be decomposed as the disjoint union of the cones k, gamma, omega, and p, where p runs over all the enriched structures on the graph. So this is quite a remarkable proposition. And now I can state the main theorem that we proved using tropical geometry. So remind that we had this diagram. So we had mg bar and the blob due to Minot, eg bar. And in here, we have the point representing a stable curve, and the fiber was EC bar. So the main theorem, and this is actually a joint work with Alex Abreu. So it consists of 2 parts. The first part is dedicated to tropical geometry. So if we define EG tropical as the union of these cells up to a holomorphism group of gamma, omega, and p. So following the proof due to Branetti, Melo, and Viviani, we can prove that it is a sticky fan. With a map of sticky fans EG tropical to MG tropical. So it is a forgetful map. So this is the first part of our theorem. And the second part of the theorem describes EC bar as a toric variety. So second part. Define delta gamma for a graph as the set of k, gamma, omega, and p. So these cones. We can take the closures of these cones and we mod out by the unitary vector 1, 1, 1, and 1. So these collections of cones actually is a fan. And actually, the toric variety associated to this, and if C is a stable curve, with dual graph gamma, so the toric variety associated with this fan is C bar, is isomorphic to is C bar. This is the toric variety. So we can describe EC bar, the fiber of the blob performed by Minot, as a toric variety using tropical geometry. And indeed, if we come to the two examples, so this was the second example. So this fan can be obtained simply by projecting down to a plane which is orthogonal to the unitary vector. So we have this plane. And if we project down these cones, we exactly obtain the fan of the blow-up of P2 in 3 points. That I remind you that it was exactly the fiber of the blow-up due by Minot over a curve whose dual graph was the circular graph with 3 edges. So this explains this figure, how to compute this fan in general. And so this is our theorem, and it was all I wanted to say. Thank you very much for the attention.